If your facility runs around the clock and you're buying electricity from the grid and separately buying fuel for a boiler, there's a version of that same exact operation where one fuel source does both jobs at 75% total system efficiency instead of two separate systems averaging around 50%. That is what combined heat and power is. I am Daniel Burke, and this is Energy Answers brought to you by Tactical Energy Group. Today, we're decoding combined heat and power, also called cogeneration. And the decision question is, should your facility invest in a CHP system to reduce energy costs and strengthen operational resilience? So here's the short version. CHP is the concurrent production of electricity and useful thermal energy from a single fuel source located at or near your facility rather than at a remote power plant. Because the system captures heat that conventional generation wastes, it can run at 65 to 75% total efficiency versus roughly 50% when electricity and heat are produced separately. So the question for your operation is whether your facility's load profile and capital position are actually in a place to support that investment, or whether the math falls apart before you even get to the permit application. This episode is for operators and executives at facilities where the electric bill and the fuel bill together represent a significant expense. Industrial manufacturers, hospitals, universities, large commercial facilities. If your combined electricity and thermal spend is in the seven figures annually and you run consistently, this episode is absolutely for you. What we're working through today is not just a technology showcase. It's about capital allocation decisions with a 3 to 7 year payback window when designed correctly. And the criteria for whether it's designed correctly are very specific. And we're going to get into that. So, what's actually happening inside a combined heat and power system? Every system has four parts: a prime mover, a generator, a heat recovery system, and controls. The prime mover converts fuel to mechanical energy. The generator converts that to electricity. And the heat recovery system is what makes CHP different. It captures thermal energy from exhaust or cooling water that conventional generation simply throws away, and it routes it back to a productive use like steam, hot water, or process heat. Now, which prime mover fits your facility? Reciprocating engines cover 50 kW to 5 megawatts. They run on natural gas, propane, or biogas, and recover heat from exhaust, jacket water, and lube oil. Combustion turbines cover 1 megawatt to 250 megawatts and up and suit large applications with hot exhaust recovery. Now, steam turbines fit facilities already running process steam like paper mills and chemical plants. Microturbines run 30 to 300 kW. They're compact with low emissions, suited to smaller commercial sites. Fuel cells offer very high electrical efficiency and ultra low emissions, but they remain emerging at a large scale. Now, here is the variable that makes or breaks every CHP project: load match. The economic case requires a sustained, coincident demand for both electricity and heat. If the thermal load is seasonal, highly variable, or significantly smaller than the electrical load, the efficiency gains simply collapse. An office building with strong daytime electrical demand but with minimal summer thermal load will waste most of the recovered heat. Where a 24/7 manufacturer with consistent process heat demand, a hospital with continuous sterilization and hot water load, a university with year round steam needs, those facilities will fully utilize both outputs. As a rough standard, projects tend to pencil when facilities run at 6,000 to 8,000 hours at least annually with coincident thermal demand. But operating hours alone do not determine viability. Spark spread and thermal utilization do. A facility at 6,000 hours with a strong spread and high thermal utilization can work. A facility at 8,500 hours with a weak spread cannot. So, what numbers do you actually need to run before you call a consultant or design a project? The spark spread is your first project. It's the difference between what you pay per kilowatt hour for grid electricity and what it costs to generate that same kilowatt hour from on site fuel at 12 cents per kilowatt hour for grid power and $1 per therm for natural gas. The source example that I'm looking at uses an effective heat rate of 4,000 BTU per kilowatt hour, but that figure already credits the recovered thermal energy displacing your boiler fuel. The raw engine heat rate is closer to 9,000 to 10,000 BTU per kilowatt hour. Your effective spark spread only materializes if you actually use the recovered heat. If you do, the fuel cost per kilowatt hour generated drops roughly to 4 cents, and your spread is 8 cents. If you do not, the math looks entirely different. Now, beyond spark spread, track your overall system efficiency target of 60 to 80%, your capacity factor, your thermal to electric ratio, and a realistic payback period, typically 3 to 7 years for C&I projects. Now, what are the risks that actually kill these projects after somebody gets excited? Capital cost is the first hurdle. Industry benchmarks for reciprocating engine CHP run roughly 2,000 to 4,000 per kW installed. So a 1 megawatt system is in the range of $2 to $4 million at those benchmarks. Though recent equipment and supply chain conditions have pushed installed costs higher, unfortunately. Microturbines tend to run higher on a per kW basis than reciprocating engines, so do not assume their smaller nameplate size means a proportionally smaller budget. Interconnection with the utility can involve lengthy negotiations, costly subsidies, standby charges, and exit fees, and is often the longest item on the project schedule. Fuel price volatility, specifically natural gas, can erode the economics. Maintenance is a very real and ongoing consideration. And if your facility's loads consolidate around a different process, or you expand or you contract, a system sized to your previous load becomes a stranded asset in many cases. So here's the thing: the resilience argument for CHP is very underweighted in most vendor conversations, and the load match problem is underweighted in most pitches. A vendor walking in with a pro forma will show you the savings. What the pro forma often does not show you clearly is what happens to the economics when your thermal load drops in the summer, when natural gas prices run up, or when interconnection standby charges from the utility eat into your net savings. Those are the questions you need answered before the capital request goes to the board. Now, for hospitals and data centers specifically, islanding is the ability to disconnect from the grid and run on the CHP system during an outage. Well, that can deliver operational value that exceeds the direct energy savings. And that's a real number worth considering and modeling for your facility if it applies. Now, obviously, I don't run your facility. That's your job. But my job is to bring you definitive answers to the most pressing energy questions facing commercial and industrial operators like you. At the end of the day, CHP delivers strong economics for facilities with high, consistent thermal loads, 24/7 operating hours, high electric costs, including significant demand charges, and reliable fuel access. But the economics deteriorate quickly when load match is weak, when fuel prices rise, or interconnection costs come in higher than projected. So here are the questions I would take to your team this week. First, what does your hourly and seasonal thermal load profile actually look like? And how many hours per year does a meaningful thermal demand exist simultaneous with your electric demand? Second, what's your current spark spread, the gap between your all in cost per kilowatt hour for grid power and the fuel cost to generate that same kilowatt hour on site? And does that spread hold if you credit only the recovered heat you will actually use? That's how you have to do that calculation. Third, have you had a direct conversation with your utility about interconnection requirements, standby charges, and any exit fees that might exist before you model the project economics? Fourth, if you pursue this, do you have the internal operating expertise to maintain the system, or does a service contract need to be in the budget? And in the pro forma from day one. Hey, if today's episode got you thinking about a CHP project you have in the works or one you might be planning, I want to help. Me and the team at Tactical Energy Group created the Energy Decision Blueprint for exactly the situation you're in. If you're an Indiana based commercial or industrial operation spending five figures or more on electricity each month, here's how it works. You and I will get on a call together and I'll learn all about your situation and figure out as quickly as I possibly can if I can actually be helpful to you. Now, if I can, we'll pull your electric bills and any interval data, project documentation, pro formas, models you have around the endeavor. And then my team will crunch it and give you a full opinion whether the project is optimally suited for your operation, whether the payback will actually materialize, whether the vendor's model accounts for your specific rate and load profile. We'll go over all of that in a follow up call, and you'll get the write up with no obligation to anything else whatsoever. If the energy decision blueprint process interests you, click the link in the description below or go to tacticalenergygroup.com and look for Energy Decision Blueprint. Thank you for listening to Energy Answers, brought to you by Tactical Energy Group. If this helped, send it to another operator you know who's dealing with the same energy headaches, and visit tacticalenergygroup.com to get more practical tools for your facilities.